first speaker is Catharina Zich. She's currently a postdoc with Nick Ward and Sven Bestman at UCL in London. And her talk is titled Dissecting Transient Burst Events. So Catharina, just...
Can someone confirm that you see my title slide?
Yes, we can see everything.
Cool. Yeah, thank you, Chris, for sharing the session and also for this introduction, so I can immediately dive into the details. So one of the most common signatures in electrophysiology, which is MEG, EG, EcoG, LFB, is differences in power at, for instance, specific locations in the brain or specific frequency or frequency bands. So here we can see a classic power spectrum, and in red we have an increase in power relative to a reference black signal, and in blue we have a decrease in power relative to this black reference signal. So this power increase or power decrease is very common, as I said, and unfortunately the mechanisms of this power increase or decrease can be manifold. So a power increase can have several causes, as well as a power decrease can have several causes. So the importance of identifying these underlying mechanisms is crucial for basic, but also especially for translational and clinical science. So one way of looking more into this and analyze which kind of mechanism is underlying this power increase or power decrease, people can use burst analysis. So a burst is a short transient event in high power. And people have looked into this to, as I said, investigate increases in power and the underlying mechanism of this. So let me quickly walk you through to some temporal domain characteristic of burst events. So here we see a reference signal which contains 3 bursts, and then we have 3 different scenarios: event amplitude, event duration, and event interval time underneath each other. So in each of these scenarios, we have a red line, which is always indicating an increase, and a blue line, which is always indicating a decrease relative to the black reference signal. So for the first scenario, we see an increase in amplitude of these bursts relative to the black reference, and a decrease in amplitude in blue relative to the black reference. And then on the right side of the small plot, this is the power spectrum, which is directly derived from this time series. So underneath, we see event duration. Again, in red, we have longer bursts this time, and in blue, we have shorter bursts and the respective power spectrum. And then on the bottom scenario, we have event interval time, which means we have events which have shorter and events which have a longer time between each other. And again, the power spectrum on the right. So clearly the left panel looks very different. So the scenarios, event interval time and event duration, clearly differ on the left side. However, the power spectrum of these 3 scenarios are very comparable. So this goes back to the point I made earlier of saying an increase in power can have different underlying mechanisms. So clearly the work of looking at bursts in the temporal domain has already advanced the field in basic and translational science. To give one example, for instance, adaptive deep brain stimulation has been developed, which is based on burst analysis and led by Tinkhauser and Peter Brown. It's deep brain stimulation for Parkinson, for instance. However, so far, all this research which has been done has always focused on the temporal domain of the bursts and has kind of reduced the spectral and the spatial domain. However, we know that electrophysiological data always have a temporal, spectral, and spatial domain, and that bursts probably also exist in a spectral domain. So here, for instance, we see again a reference data. It's 3 bursts around 20 Hertz. And then we also can characterize the spectral domain by having spectral domain characteristics such as event frequency spread. So here we see events which have a wider frequency spread than the black ones indicated here. And here we see events which have a narrower frequency spread. Similarly, the spread could be the same, but the event might be at the upper level of the frequency or the lower range of the frequency as indicated here on the bottom by changing the event frequency boundaries. So there are more of these event characteristics, and they can also interact within and across domains. So for instance, an event which has high amplitude might also have a longer duration and a wider frequency spread. This is obviously a subject of investigation, but I'm only highlighting here the main characteristics and not necessarily the interactions. So then also bursts will have access or will have a spatial domain and will exist in space. So again, we have here our reference data. So bursts might exist in this location in the brain. Bursts might be wider or smaller So the spatial width can be a parameter, and depending on the location, the power spectrum might actually change or might be similar. Also, spatial width can be the same, but the location might change in space. So bursts might be more anterior or medial or posterior or lateral to a reference position. And again, depending on the position, the power spectrum might change or might be identical. So the main point I want to make in this first part is that burst event is a very interesting thing to investigate and might be extremely helpful to investigate further differences in power. But so far, people have highly focused on the temporal domain of these burst events and ignored the spectral and spatial domain by reducing the spectral and spatial domain before analyzing the temporal domain. So in the next couple of minutes, I want to talk about what these domain reduction might do to the data. So here we see MEG data from a single trial in this case. So the data are button presses. So 0 is locked to the button press. So we would expect higher power post-movement compared to pre-movement. So it continues with the classic ERD-ERS pattern. So these are data from the motor cortex, and we're looking at the beta frequency band. So in this first panel, it's always the same trial, and I've already reduced the spatial domain just to keep it one domain simpler. So we're basically looking on the effect which it has if we reduce the spectral domain and how we reduce the spectral domain on the temporal burst characteristics. So in brown here, we see the average beta power of this M1 passer. So taking the average of a frequency band is a very classic reduction method for reducing spectral domains. So here's the same data in green, but this time it's reduced by taking the beta peak frequency rather than the beta average. And again, already we see that the time course looks very different, not only in its amplitude, but also in its profile. Here on the third, we basically don't have a reduction, but we see the frequency and we see the power on a time frequency plot with frequency on the y and time on the x-axis. So we clearly see 2, potentially even 3 bursts depending on the threshold. So if we then binarize these different data, which is often done for burst analysis, and we stack them on top of each other, then we can see that depending on which reduction method one uses, the temporal characteristics are clearly distinct. So here I visualize the same again, but using a different trial. And now we look at the temporal spatial interaction. So basically how the temporal properties change depending on how we reduce the spatial domain. Now we look at the average of the whole beta range, so just to fix the spectral domain to have a little bit easier. So here again, we see the first principal component of a voxel. So it's a common method to reduce space. And then in green, we see the peak voxel, another common method to reduce the spatial domain. And here we see now power displayed on the y-axis, we have voxels in the M1, and on the x-axis, we have time. Again, if we binarize these data and stack them on top of each other, we clearly see that the way how we reduce our domain influences our temporal properties. In addition, we also clearly see here that this event potentially travels in space. So we might see that depending on the time the spatial location might be slightly different. So this already means that regardless which reduction method we use, we might underestimate the true time of this event because it is basically traveling in space. So this gives an indication that even if you're only interested in one domain, so let's say the temporal domain, considering all domains enables to account for these interactions and potentially have a clearer estimation of the true burst characteristics. But these interactions can also be highly interesting. So for instance, here I show data from one single burst. So this is not the average of a couple of trials or a couple of bursts, it's literally a single burst. So the burst is located here in the sensor motor cortex. And here we just have a zoomed in image of this burst. So everything which is colored is basically part of this burst. And then the color code, everything which is not gray, is depending, it shows us when this burst peaks. So everything which is brown peaks earlier in time, and then towards greenish peaks later in time. So one could say, oh, this burst might travel from an anterior towards a posterior position. So here we potentially see a temporal spatial interaction. On the panel next to it is exactly the same burst. We just look at a different set of features. So here we look at the spectral spatial interaction, and we see that this part of the burst, which is more anterior has a higher peak frequency, and the part of the burst which is more posterior is kind of lower peak frequency. So this is kind of like a static image of this burst, but we can also look at this in a dynamic way by looking at this video. Where one sample is 50 milliseconds, and we can see how this burst evolves over the cortex and how the other features evolve with the burst in time. Just play one more time. So to summarize, I hope I could convince or remind us again that bursts exist in 3 domains, and that these 3 domains can be characterized with main domain characteristics. For the temporal domain, for instance, with event duration and event interval time, for the frequency spread, and upper-lower frequencies, and for the spatial domain, spatial width and spatial location. I hope I could show that the domain reduction can potentially deceive depending on which domain reduction is used and if there are interactions in the data, but also that these interactions can be potentially meaningful and interesting. So this, thank you for your attention.
Yes, thank you very much, Catharina. Very interesting talk. So again, if you have questions, put them in our Q&A window. Maybe we'll wait for a couple of seconds if people want to ask questions. Okay. So no questions from the audience, but maybe I'll ask one. I guess that's totally independent of the frequency band you're looking at. I mean, you have basically exemplified everything in the beta band, but are there any pitfalls or something we have to look at when you go to very low or very high frequencies? Maybe comment on that.
I think I'm personally kind of, my background is like sensory motor beta activity. So for me, like it's like I'm using the sensory motor beta activity to basically showcase the concept. But I think it's similarly true for like lower frequencies, higher frequencies, like theta, gamma, alpha, and or different regions of interest. So we could like look at like, I don't think why this should not apply in like visual alpha, for instance. So yeah, I think that's kind of like pretty universal.
So then we have a very basic question from Lena. So she says, I'm very new to this, but do you have some references to suggest for preferred analysis methods?
I think I would always start with like the groups who basically started the burst analysis. So I think I would go to like Stephanie Jones' group, and like there's a paper in eLife from Shin in 2017, and then from there, there's basically it's easy to find the rest of the references. I guess it's a good starting point.
Lena, just get in touch with Catharina by email or so, and I guess she can give you some more information on that. So thanks again, Catharina. It's time to move on to our second speaker.